Anatoly Konechny from Heriot-Watt University in Edinburgh, who will be telling us about topological defects and constraints on our G-flows.
Thank you, Andy. And I'd like to start by thanking all the organizers for their hard work they put into putting this program together, and also this conference. I've been really enjoying this. So part of this talk is based on a joint work with Vasileios Verchioglu, who just finished his PhD in August, and he's currently looking for postdoc position. So my plan is to be pedagogical. So we'll go over various old and oldish results, but I'll also mention a few newer things. And I'll stay in the context of two-dimensional perturbed conformal field theories, and I'll take my perturbed theories as rational CFTs. I'll perturb them in the bulk and on the boundary. So I'll start with bulk RG flows, and we'll just discuss what constraints can you get from topological defects there, and I will use the language of RG boundaries for massive flows. Then I'll switch on to boundary and defect RG flows, and there I'll discuss junctions with topological defects, junctions between defects and boundaries, and then what constraints you can get from those. And then after this, I'll mention some interesting mathematical problems which arise when you just try to construct systematically local fields which commute with topological defects, so you can ask these kind of questions. And I'll finish off with some open problems, although along the way I'll be also mentioning things, say, I don't know, and I think it would be interesting to work out. So I'll be working in the framework of rational CFTs, which are, the representation theoretic structures is described in the formalism of topological field theory, which leads to the notion of modular tensor categories. And as Christoph yesterday reminded us, this stuff is already 25 years old, quarter of a century, the way he put it, and he talked about extending that old formalism. So I will stay with the classic stuff, with the old stuff, where we start with, so our symmetry is described by this modular tensor category C, in which I have a finite number of irreducible objects. So here I label them as phi i's, and they form a ring, right? So you can take a tensor product, and there are some structure, integer structure constants here. If one takes this C and one wants to construct a full-fledged rational CFT, one needs to, so this C is responsible for chiral algebra representations, so we need to glue them, the left movers and the right movers, and learn also how to calculate correlation functions. And the information of how you glue left and right is encoded in the so-called, in the appropriate Frobenius algebra objects A, which are objects in the category C equipped with appropriate multiplication and co-multiplication. And then we can, so once we have chosen our Frobenius algebra object A, we essentially can construct all correlation functions. And besides the correlation functions of local operators, we can also describe conformal boundary conditions as the A modules, and topological defects as AA bimodules. And so once you have these bimodules, you can construct for them a fusion rule as well, which has the same structure, but in general, if your A, depending on your A, this, it has the same form, but the structure constants can be different. in principle, from the structure constants in your symmetry algebra. Things simplify if you take the trivial Frobenius algebra object, which corresponds to just charge conjugation modular invariant, when you glue left and right movers in the simplest possible way, then the two rings are the same. Moreover, the fusing matrices for both for C and for this bimodule category are also the same. So things simplify quite drastically in that case, but in principle it is interesting also to consider defects and learn how to calculate this and the appropriate fusion rules. It's all known in principle, but you know, for some even basic examples, I don't know the answer for some of this. For example, what are the fusing rules? Here, you know, even like get a closed formula for the free boson. I've never seen it. So, so yeah, suppose now, well, in a generic situation, we have a CFT and we have local bulk operators, and we have a topological defect line X here. Then we can take this line and sweep it across, passing through the defect. So we will surround the defect like this, and then we'll shrink this to intervals to bring it to this picture. So in this picture, I have isolated a local term, where you can think of it that there's just an identity trivial defect between the insertion and the defect which passed through. And here we have the non-local terms, right? So they will look like this, because now after the sweeping, I will get these contributions where my operator phi is no longer local. It has the same filter, same quantum numbers, but it lives now at the end of a defect. So what will be of particular interest for our G-flows is the case when there are no non-local terms. So suppose you just the first term is here, and here you have nothing. So we'll discuss in the end like how you know, one can try to systematically find all such cases. I'll address this problem, but okay, there are many known examples. So this case is of interest to me, and if it happens that this bulk operator it is relevant, then we can deform this CFT by switching on the perturbation by this bulk relevant operator, and then this topological defect it will commute with all the multiple insertions. And it will remain in the perturbed theory also as a topological defect which you can move freely around. And it should, if you normalized it, then it should survive into the infrared. So this situation, is, I guess, I mean, I'd like to compare it briefly with what Sakura considered yesterday. She considered a more general question. Again, we start with some SIM-TFT in the UV. I mean, in this context, that SIM-TFT will describe these topological lines, and then the question is, what can, in principle, survive in the IR? It was done in a broader context, and she didn't even, you know, include any particular perturbations, and she didn't require that you have, you know, the commutation relation, right? So it was just a more general framework. So I'm doing something like more, I guess, more concrete here. At least I know if I have such a commuting pair, something is there and something should survive. So that yes?
So what is wrong if there's a non-local term present? What happens?
Well, then, so because you imagine you, I mean, you want to have a topological defect in the perturbed theory, which means that I should be able to move it through all the local correlators. So I just won't be able to.
So it would kill exactly these topological lines, basically.
Yes. Yeah. So.
We still want ones that survive.
Well, okay. There may be other ones which will emerge just in the infrared. I don't know how to control those, what to do about them. Partly, I think Sakura partly addressed that question. Some selection rule there. Also, yeah, as you said, if there are non-local terms, I don't know what's their fate. And this, certainly after I switch on the perturbation, they're not topological defects. I cannot think of them as topological defects of the perturbed theory. But these ones which commute, if it happens, then they're like charges which are conserved for me. Right. So another interesting case is when it anti-commutes. So it can happen that you pass through and it's multiplied. Yes?
But in general, shouldn't you have the quantum dimension of the line, not just the negative delta? Like the line commutes with the operator, but it leaves behind some factor that's the quantum dimension of the line.
Oh, yeah, okay, yeah, you're right. So the normalization here, it depends on what normalization. Yeah, okay, if phi is the same, then yes, this can be proportional to a number. Yeah, you're right, but okay, but I significantly distinguish positive and negative numbers here. So I'm talking about anti-commuting ones. No, I don't think so, because I'm not starting with a bubble, which I just say create, and then I should divide by the conformal dimension and then sweep it through. But okay, I forgot. Right. So that's another interesting case, and so the consequences were discussed in this paper from 2018, which is a very nice paper. There's a lot of discussion of topological defect lines and particular applications to concrete RG flows. So in particular, they noticed that if it anti-commutes, then there should be a defect. So then you have a defect between two different infrared fixed points, one to which you flow with positive coupling and one to which you flow with negative coupling. So there's still something nice you can say about that. So I'd like to discuss this in more detail, but before I want to introduce the object of RG interfaces. So the idea goes back to the work by Brunner and Rogenkamp, who just proposed to consider perturbing a CFT on a half space and then renormalizing it and then seeing where that can flow. So you can think of it as a deformation orbifold, but since, deformation interface, but since you can follow along the RG flow with it, and at the far infrared you expect that everything will be conformal, scale invariant, and then conformal, then what you get you can call the RG interface. It's like a remnant of the RG flow. It's a conformal object which is left behind the flow. And if the theory, the perturbed theory is massive, then what you expect is actually that this interface will look like a conformal boundary. So here's an intuitive argument of why is it true. So suppose here in the blue part we have a CFT, and in the red part we have a perturbed CFT, which we know is massive. Then there is a mass scale here. Then we can think of hypothetical scattering experiment. I know that it's difficult to talk about particles here, but we can form, for example, like a wave packet of finite energy of stuff, and then throw that wave packet at the interface. And then we know if the energy of that wave packet is less than the mass, then it cannot create, it cannot go through. There's no transmission. So you should be bouncing back, be fully reflective. And in particular, if you go into the far infrared, when this mass becomes larger and larger, and you're focusing on the scattering experiments with small energy, then the effective theory will be that of a boundary. So it really will look like a boundary. And then, of course, if you cranked up all of your scales, no scales in the theory, this boundary must be conformal. So this I will call this conformal boundary an RG boundary. Right? So these RG boundaries, they describe gap phases. I mean, I think this is probably like almost trivial to some people. I don't know, I'm looking at Frank, who is probably, who is usually what people, but I've heard many questions at at other conferences, like some people get puzzled, like why massive phases can be described by conformal boundary conditions. So that's my best explanation, but apologies if someone thinks this is just a triviality. So, so suppose we're massive, the RG flow leaves behind this conformal boundary condition. It might be degenerate, and that would correspond to a spontaneous symmetry breaking phase. So when this boundary is a superposition of some number of boundaries, so that's also an interesting effect. So now, okay, now that I said that, so we have boundaries in the game, conformal boundaries, and we have also topological defects. The one thing you can do is confuse the two of them, and you get another conformal boundary condition. So, so now we can formulate actually what are our expectations in the infrared. So if you switch on just one coupling, you can flow in two different directions, positive or negative coupling. If both phases are massive, then there should be some conformal boundary states corresponding to them, possibly degenerate if there is spontaneous symmetry breaking. And then if you have any commuting topological defect lines with the perturbation, so those should be present in each infrared phase. If you have the anti-commuting ones, then they should be junctions between the boundary conditions on both ends and this topological defect. So I'll tell you more about junctions now. So that's how, oops, sorry. So that's how a junction looks like. So if I have an anti-commuting topological defect line, I have this situation when from the UV I flow to the massive phase 1 minus, and it's described by boundary state, conformal boundary state with a minus, and then I flow with the positive coupling to the plus. Then if my TDL anti-commuted with, if it anti-commutes with the bulk perturbation, then there should be a topological junction like this. And in your CFT, there are constraints on when such junctions are possible. So they're not possible between, so they're possible between any pair of boundary conditions, but they're not always topological. So you can have you can always end a defect line on a conformal boundary of any kind, but the endpoint might be a non-trivial operator, will have some conformal weights. But so it's a stronger condition when it ends topologically, and that's what we expect here.
Sorry.
Yeah.
By this anti-commuting case,
Yeah.
one particular example, if you just have a T2 symmetry,
Yeah.
and then you have an operator that is charged on the T2 symmetry. So in that case, I would say that the symmetry is broken.
Right. Okay. Yeah, but then you would expect that there is. Yes, it is broken. Therefore, you will flow. Yeah, this symmetry will actually map IR plus to IR minus.
Yes.
That's the simplest case.
Yes.
Sure, that's what happens.
So the boundary condition is never invariant under a symmetry.
No, if it is, if you have a symmetry preserving, if it commutes, then this boundary condition, you fuse with it, it must be invariant.
What is the reason to distinguish this case from a more general case in which you just have an operator that breaks symmetry? Say you have a Tn and you have an operator that breaks Tn. Why is this T2 case more special than that?
No, did I say that? No.
It's not more special, okay.
I don't think so. Moreover, I mean, I think more interesting constraints come from non-invertible defects. So, yeah, I mean, you can look at symmetric ones. You can easily guess.
The case in which you do break the Tn.
Zn, so you want now like Z3 or?
Yeah, I'm asking why is like more special than the most general situation in which you just break the symmetry?
No, you can, I mean, in general, yeah, I'm kind of confining here myself, I guess, because it's plus and minus, I'm confining myself to some simplest case, but in principle, you can have an action which will multiply by a phase, or you can have a multiplet, and this multiple is rotated somehow of fields with the same dimension, so yeah, there can be more. No, I'm just kind of here, not trying to discuss sort of the most general, the full generality, just kind of convey some basic ideas, but yeah, they can be, everything can be sort of generalized. Yeah.
Can this TDL just transform the boundary? Because I can view boundary as a boundary state. So if your TDL fused with a boundary, you can view this symmetry transformation, right? You get some phase in general.
Well, you cannot multiply conformal boundary conditions by a phase, or by a number. I mean, yeah, all you can do is you can switch on a local operator, but then it will run. It will be like, you switch on the identity operator, for example, it will be, you cannot, I mean, you can only have an integer superposition, right, of conformal boundary conditions. You can have, plus 2 minus, but you cannot have plus and, some kind of exponential, or even negative real numbers also, they're not making sense, so. Right, so here's an elementary example. For example, yeah, if we start with the critical Ising model, then we have two TDLs. Here we have the Z2 symmetry and the Kramers-Vanier duality. And then the thermal perturbation, it commutes with the Z2 symmetry, but it anti-commutes with the Kramers-Vanier duality. We have three elementary conformal boundary conditions correspond to spin plus, spin minus, and the free boundary condition. And then here is the action of the TDLs. So the Z2 charge, it just exchanges plus with minus, but leaves free condition stable. And the Kramers-Vanier, when it acts on F, it gives you plus minus. So yeah, the classic example of spontaneous symmetry breaking cases, so we perturb the critical Ising by this thermal perturbation. Okay, the coupling sign is conventional, but then say here on this picture, the convention is such that for the positive case, we flow to the disorder phase. For the negative coupling, we flow to this symmetry breaking phase. And the assignment of the boundary conditions like this. Each one of them is Z2 symmetric, but the one on the left is a superposition. So that's what we observe from Z2 symmetry, but from the Kramers-Vanier duality, which anti-commutes with the perturbation, you see that that defect can be attached between these two boundary conditions in a topological manner. And you also see it, yeah, as I showed before, if you act by Kramers-Vanier on free, then you get plus minus. So that guarantees basically that it can be attached. Things are also, what can also happen is that you can flow to, you can have a massless flow, and you can flow to a non-trivial CFT. This is described in my second example, which is in the tricritical Ising model. So here we have 6, I think it already appeared in Yifan Wong's talk yesterday. Yeah, so there are 6 primary states and there are 6 boundary conditions, which in the Bloom-Capel language of the lattice theory, where you have your discrete parameter, which is either +1, -1, or 0. So you can show that you get these boundary conditions. So you can have either spin plus, spin minus, or spin 0. Or spin 0 plus means essentially that either 0 or plus is allowed on the boundary. And D, well, you could probably think about it as some free boundary condition, although traditionally it's denoted by D, which is for disorder or discrete. You can choose. So here, an interesting perturbation is by phi epsilon prime, which commutes. So this is the Z2 charge. So it commutes with Z2, and this is the Kramers-Vanier. So in this example, there's also Kramers-Vanier duality in the tricriticalizing, and in this example, the perturbation commutes with both the group and the duality. And here are the fusion rules. So what you expect? So you get the so it turns out that in one direction this is a massive phase, and that's triply degenerate. And this is this is built from the superposition. It is described as a superposition of these three conformal boundary conditions, and you see again it's Z2 symmetric. But in the other direction, you flow to the criticalizing model, and okay, you can no longer use this boundary language. Instead, it's a conformal interface, which was constructed by Gayotto some time ago. So I call it Gayotto's interface here. So in general, in this business of just using TDLs, you can, I'm not aware of a kind of nice method which just algebraically would tell you whether you flow to a massive theory or massless theory. I mean, that's in principle kind of an open question. I think you need some more input. Have some kind of conjecture here of what, how to select it, but it would be nice to have something like this, just because we have very few examples of conformal interfaces, right? So you cannot just start kind of looking around for all possible interfaces and see if they are compatible with the preserved TDLs. It's just not very realistic. So it's okay. So just want to point out that there's I think an important problem here of finding, characterizing when do you expect non-trivial and when it is massive. But so in this case, so these two guys commute, so they both should survive in the infrared. And in the case of the Ising model, their subalgebra is exactly this subalgebra of the TDLs in the Ising model. So they exactly realize Z2 and duality fusion algebra of the Ising model. So either you get this kind of condition on the boundary, or characterize it like this, or there's another approach which I'm not talking about, but I want to mention, by Sakura and her collaborators. So they focus their attention, instead of the conformal boundary states, they focus their attention on, they develop the generalized Landau paradigm, so they have kind of a generalized order parameter, which forms some multiplet and includes some defect fields, and they look at the action of the surviving TDLs on the order parameters there. Okay, so that's also interesting. And here, yeah, I'm citing their papers. Right, yeah, there's another, this is also a nice paper. So, yeah, there's this work. Right, so now let me turn to boundary RG flows. So here I first want to mention this old result by Jared and Kevin Graham here, which to the best of my knowledge is the first example of when TDLs were used in conjunction with RG flows, and some interesting results were obtained. So as I already mentioned, you confuse a TDL with a boundary condition, but now imagine you perturb your theory, so this is no longer conformal, then they showed that you confuse and you get a different perturbed theory, so now you can think of it as a different, as a perturbation of the fusion of X with the underlying conformal. So with the underlying conformal boundary condition. And so this way you get a mapping from RG flows, from boundary RG flows to themselves, which has a rather nice structure. So if we now use the G theorem, if I kind of map, So this is G running vertically. So if I have a boundary flow from some UV boundary condition, and then it flows to some IR boundary condition so that the G factor decreases, then if we fuse it, and if this X is not group-like, then the boundary entropy will go up. So then you can picture it as some kind of flow. The fused flow will look like this, higher up, which starts from some UV2, IR2, and you can lift that one further on because you can keep acting by all the non-invertible TDLs you have. So you will generate a sequence, and so if you want to find the endpoint for some particular boundary RG flow, it might be a good idea to say, can you strip off some of these actions? It's not always possible, but if it's possible, then you can go down to the lowest possible G, and that's nice because if you if you know all your boundary conditions, you know all your possible endpoints, then the lower your G is at the starting point, the fewer possibilities you have for your endpoints. So for example, you can use this nice result like that. But that's sort of, so it has a different flavor. It maps, like in the bulk, we could say something about a flow itself, or connecting flows in two directions of the coupling, related to the coupling sign. Here, we relate different flows. But if you want some constraints on a particular flow, not appealing to other flows, just on itself, then you can look at the topological junctions. So maybe I want now to say just a couple of more words, since I already mentioned Frobenius algebra object, and I mentioned that conformal boundary conditions are modules, topological defects are bimodules. Then such a junction can be mathematically described as this kind of home. So we are now in this kind of objects. So they are, all this, the machinery of the TFT applies to junctions as well. And one thing which is interesting is the analog of the sweeping through operation. So now here I have a boundary operator, and here I have my topological junction with a defect, so I can lift it up and pass through. So in general, so that will generate here a sum. So part of this sum runs over this index D is the intermediate boundary condition. So they can be different. So that will look also non-local. And this sweeping through is governed by a particular set of coefficients, which in general, again, this is some kind of different type of fusing matrices. But if you're in a charge conjugate theory, then it's again just the ordinary fusing matrices. So the interesting case here is when the only contribution is the sum is from the old boundary condition, which was between psi and the junction. And then again, the simplest situation you can imagine is that it's multiplied by plus or minus 1, so it commutes or anti-commutes with the TTL junction. Another thing which is interesting here is that you can fuse two of these junctions together. Again, it's governed by some type of fusing matrix. With Vasilis, in our paper, we used the notation T because sort of we were thinking about some rationale, because everybody tries to use F, and then there's F twiddle, F check, and F prime. And then it's kind of hard to get sense of all these fusing matrices just looking at the symbols. So I want to advertise T. We thought like the junction looks like letter T. So let's use T there. While in the previous example, we put a dot here because we were thinking, oh, dot is where the boundary field is sitting. So we tried to, but I think everybody sticks with their notation anyway, their favorite notation. So you have this kind of fusion operation, And that's, in principle, you can think of it, that it replaces the fusion ring in the bulk. But you can think of it like this, but it's important to realize that this is no longer a ring. This will be in some non-associative structure, right? So this is like a fusion matrix, satisfies some pentagon type equation. So when you start kind of lumping these charges together in this fashion, then you get something non-associative. While there is a way to make a nice associative algebra from these charges is that if you put everything on a strip. So if you now have a strip with some boundary conditions on both ends and you run your topological defect line from boundary to boundary, so you have a junction here and junction there at both ends, then you can fuse them together and it will involve this matrix T twice. So T bar here is the inverse. And it turns out that this fusion is associative. So it's a nice associative algebra. And you can think of it as replacing the ring of just fusing bulk topological lines. Being finitely generated, this as an algebra is an associative finitely generated algebra, so it just breaks up into a direct sum of matrix algebras, where each direct summand corresponds to an irreducible representation. Yes?
Can this be interpreted as some boundary anomalies?
I think the previous guy, yes, the one end fusion. It's like fusing matrices. You could. No, but this is just an associative algebra, so it's kind of just nice to think that your charges you can multiply them as if in an algebra.
So maybe previous.
Yeah, in this picture, they just have some. I mean, so if in general, if you have like a hierarchy of different fusing matrices and there are different pentagons between them, so it's like a whole host of relations. I think, like in some generalized sense, you can think of them as some anomalies, but I'm not sure. I don't have like precise words ready here. Right. So. But there's a caveat here. So you think, okay, it's a boring thing. It's just direct sum of matrix algebras. But there's some extra information here. Namely, I know how my irreducible objects are sitting inside this matrix algebra. So there is some additional information which comes with it. So, but let's say for now, let's stick with this associative algebra and think of it that's if I have several TDLs, some of them may commute with the boundary conditions, and then they should survive as a junction in the infrared. But then if they anti-commute, they should be relating plus and minus, and you see quickly that, okay, if, on a strip, you have two ends, so basically you get 8 different types of this boundary tube algebra elements, which you can fuse together when it is allowed. So it's some kind of larger structure here. But yeah, if you know how it is that it is realized in the UV, essentially they should be its realization in the IR between the endpoints. Am I doing time-wise? 43. Okay, still okay. Right, so this boundary tube algebra, in the last 2 years, I think there have been quite a few interesting papers with all sorts of questions considered. In particular, it was used like as a symmetry algebra in your CFT. You can construct symmetry resolved entanglement. There's a bulk tube and there's boundary tube. So both questions were, the representation theory and how it is useful for various quantities in CFT, it was worked out in this sequence of papers. Okay, so I think I just want to mention all these papers here and then all these recent activities. So what happens? Another very simple consequence is that in the presence of anti-commuting TDLs, TDL junction, you can show that the G factors must be the same in the for the two endpoints. So now you have a coupling, boundary coupling with positive sign, boundary coupling with negative sign, so you end up with two different fixed points. They must have the same G factor, and it's I think it's fun to work with working with different concrete examples. So here, for example, let's consider a tetracritical minimal model, M56, and we look at the Cardi boundary condition, which corresponds to the representation 3-3 using the Katz table, standard Katz table notation. Then the boundary field psi1,3, it commutes with the junction L3,1 and anti-commutes with L2,1. So both of them are non-invertible. It commutes with one, anti-commutes with one. And it's also anti-commutes with the symmetry generator. In this case, the boundary condition itself is Z2 symmetric, so it makes sense to talk about charges of the boundary fields. And this field is negatively charged under Z2. The endpoints are known for all psi1,3 flows from elementary Cardi boundary conditions, and
Is that a boundary flow?
boundary flow.
I think it should be 3-2 or 2-3, because
What? The perturbation is 1,3.
if it's a perturbative boundary flow, then on one side, the sum of RS...
Oh no, it's perturbative on one side, it's non-perturbative on the
Yeah, so
other.
the sum of RS on one side should be equal to RS in the middle. So that's
This I took from one of your papers.
Yeah,
Did I do it wrong? Well, we can look it up later,
So
but
it's true with that either being 3-2 or 2-3, I forget which.
well, but mind also it's a particular minimal model, so they are identifications. So
Then you're right. Yeah, it's 2-3.
yeah, sorry.
Thank you.
But that was taken from one of your papers. So the endpoints are known, and this is yeah. So this is essentially the TBA, which gives it. But it's still fun to see how this the tube, the boundary tube algebra, or the strip algebra, you can call it, how it is realized in the UV and the infrared. So you can work out the UV relations, and so here you see immediately that you can think of it as some kind of deformation of the fusion ring, because there are non-integer coefficients here. So here everything comes out from this number f, so it's either f or 1 minus f. So the fusion rule kind of respects, so it doesn't allow you to put in anything new which was not in the bulk, but some things which were in the bulk are absent, and others are multiplied by some numbers. And these numbers, in principle, I mean, some of their combinations are invariant. So there's some invariant information here, because you do know, that you can canonically normalize these guys, and you know which ones are irreducible. So essentially, it's kind of a non-trivial, special kind of deformation. And so that's what it looks like in the UV. While you can also work out how one-end fusions look like. They look, well, pretty similar here, but one should bear in mind that in principle this is some non-associative structure if you fuse 3 of them. So that can be worked out, and then you can look at these two endpoints and see how it is realized. And then here, what is interesting, I think, is you find kind of discrete number of solutions, and not always one. And I think, so I found like three different solutions here. So everything is realized according to how it should be, from matching the UV information. But there are 3 different options. I don't know which one is realized. Maybe it can be studied numerically. But I think there's an interesting question here, maybe for mathematicians, of in general, if I have these different realizations, how sometimes it's not possible at all. Sometimes maybe there's a unique one. Sometimes there are several ones. So there's this question of how you generate them all, how you find out when that algebra, what are all possible realizations of that particular UV tube algebra you find. You can ask it about any subring, I suppose. So, yeah, well, but you can do more interesting things. For example, you can look sometimes at psi2,1 and psi1,2 perturbations for which there is no general answer known. So they're believed to be integrable, but there's no TBA, as far as I know, solution found for them, and you don't know the endpoints in particular. So here you can there are some particular examples when this matching of your UV algebra and the infrared algebra is strong enough to pin down the endpoints uniquely. So here's one example, for example. So this is a psi 2-1 perturbation. I think it's the same 3-3 and 5-6. What did I have before? Sorry. Yeah, it's the same model, tetracritical minimal model, the same boundary condition, but instead of 1-3 perturbation, we'll look at the this 2-1 perturbation. So we find that it commutes with a Z2 charge and anti-commutes with a non-invertible one. So then, of course, you also use the G-theorem constraints. So there are only a few things you can write down, but everything is ruled out except for two possibilities. Okay, so I focused on the boundary flows, but you can ask, of course, what about defect flows? Here, there's one simple correspondence that boundary flows, if we do have an identity boundary condition, as an identity boundary condition as we typically do have, say, a Cardi identity brane in the minimal models, then you can always represent an arbitrary UV boundary condition as some TDL line acting on this favorite identity boundary condition, and then we can move over your boundary perturbation onto the defect. So we can detach it from this special identity boundary condition and look instead at the perturbed defect, but the defect will be perturbed by chiral operator. So essentially, chiral perturbed defects flows is the same as boundary flows. But of course, there are non-chiral flows, which are also interesting, and in particular, the pinning defects, which were discussed by Yifan Wong yesterday. So that's such an example. So it will not be just the same as a boundary flow. So we had a talk about that. And there, for this type of flows, there are other really nice ideas. For example, the new defect anomalies were introduced by Antinucci, Christian, who was here yesterday, I think, Giovanni Galati and Giovanni Rizzi. I'm not sure if there are more people here from this collaboration. Great, guys. Sorry, I never got a chance to introduce myself. So it's a really cool paper with defect anomalies. When there are, I mean, you can talk to them and they can explain to you. But yeah, so there's more interesting work going on. So one thing I want to address, however, I haven't seen much discussed, is symmetry breaking TDLs. And one simplest example for that, or some arena for that, is Vezumin-Witten models. So we have global symmetry in Vezumin-Witten models, so which are generated by current algebras, left and right. And then we have the simplest symmetry breaking defects are the Wilson lines. Right, so they look like that, and the fusion rule, it corresponds to just the group multiplication. So, so you can choose left and right component arbitrarily, so they're all topological, but only the diagonal subset in my conventions, LGG, can be topologically attached to the symmetry preserving Cardi boundary conditions, right? And so what are they useful for is the following question. So if you consider a boundary, so if you start in the UV with a symmetry preserving boundary condition, then all of your relevant boundary operators, they carry some group representation. So if we were doing something in the bulk, we could always create a singlet from the left mover and the right mover, right? And then we would perturb in the bulk by G-preserving perturbation. Here, it doesn't seem possible to do in this naive manner. So each of your boundary fields will carry some representation of the group. And then, if you, then you will be ending up in some symmetry breaking conformal boundary condition in the infrared, and we don't have a complete classification of those. It might be just the G-twisted boundary conditions, but maybe not. Nobody guarantees that. So if you want to sort of exploit fully your algebra and stay in this class of rational CFTs and rational symmetry-preserving boundary conditions, you need some, you need to do something else. You need to consider some special flows. And here, what I would propose, so this is still some work in progress with Vasilis, but I would like to propose some simple generalization of the Kondo type perturbation. So to engineer flows which will end up in symmetry-preserving boundary condition, we start with a superposition of identical copies of the boundary condition, and then so what was my W? So alpha, right? So this alpha is the junction. So if I have here n boundary conditions, then the junction with a group defect is in general a matrix which operates there. So you can choose that matrix to carry a representation of your group G. And then if your boundary field is in the representation in the representation R of the group G, then if you satisfy this simple condition, namely alpha star R just tensor product of group representations. If it contains the identity, then you have here an invariant tensor, and you can construct a perturbation which will commute with all the group defects which are attached through this particular junction. So that's kind of, this is a simple generalization of Kondo type models. You can ask the same question in the Kondo, so why that perturbation ends up necessarily in some symmetric boundary condition? That's due to a similar construction, but this should be simpler because I can consider all relevant perturbations. Well, simpler in some sense. This will be relevant perturbations, so I will not expect some non-trivial beta function to all orders, or that beautiful story, of course, but so I can dress my boundary perturbations through these special matrices, and then I claim it's enough to guarantee that in the infrared, the flow will stop in the symmetric boundary condition. So here's the argument. So if I have my LGGs, I can think of them as like exponentiated charges. If they commute with the boundary perturbation, then if I do this infinitesimally, this must correspond to the gluing condition in which there's a local conservation law. So J minus J bar must be derivative of some boundary operator. And in perturbation theory, you can do conformal perturbation. You can work out that what this boundary operator is to the leading order in the couplings. But then, if you are at a fixed point, then you can count the dimensions. This guy should have dimension 0 because the currents have dimension 1. But then, if you assume unitarity, so I need unitarity here. If you assume it, all operations of dimension 0, they are annihilated by the translation. So this must be 0, and therefore the currents are glued locally so that you get a symmetric boundary condition. And so you can get more, you can play with this more, with this kind of flows. For example, you can look at the analogs of the RG interfaces here, which will be some special BCCs, of which many people talked, Eric and Masashi here. So after the RG flow between, you get, which starts from some UV conformal boundary condition, you get, you always flow to some non-trivial infrared boundary condition, and so that gives us a particular boundary condition changing operator, which you can call an RG operator. So if you have some commutation condition with those junctions, group junctions, then it imposes, again, certain interesting constraints. So this operator might not be always available, so you get some selection rules for which infrared fixed points are possible and which not for these flows. But this is still, as I said, work in progress. So last part of my talk, how one can try to construct commuting pairs. So let's start with the bulk. So people observed a long time ago that, I think already, at least I saw it in this old paper of Gayotto about RG defects, that sometimes if you choose your representations in a particular way, the representation for the I and I bar, which label the bulk field, and the representation for the boundary, representation for the your TDL, if it satisfies a special condition in terms of the fusion rule, that guarantees that nothing can appear here. So only the identity field will appear here. So you can phrase that condition for the bulk in a very, in a concise way, it will look like this. So the all homes from I, tensor I bar, tensor D bar, the identity field must be present there only once. If that's the case, then nothing appears here. It's really a simple thing because, so if something attaches here, then this index E must appear in the crossing of D and D bar. And then on the other hand, to end on the specific bulk field content, I and I bar must also contain it. So if the identity field is the only solution here, then no other fields can appear, no other interfaces can appear there. And you can reformulate this condition, and you can just interpret that that tensor product differently. And the equivalent condition is that I fusion with D must be a single representation. And then this question, well, although the motivation was different, but Matt, who was, I think, here yesterday, again, but not here, and his collaborators, Lee and Radhakrishnan, they actually look at all the cases of where the fusion, how to find a fusion algebra and how to find such two elements for which the fusion product is a single element. And essentially, if you have a simple current, then it's trivially the case, and one can show rigorously that in the Zumina-Witten theories, this is the only possibility. But then they looked at all other possible examples. So when you start tensoring theories or taking cosets, then more possibilities arise. So they addressed this question before, but I think there's still something maybe interesting to do here, just searching for all these commuting cases. That seems to me like the easiest way to do, just to find fusion rules which guarantee that that's the case. And similar problems can be posed for the boundary. So for the boundary, now I have more representations in the game, so it's slightly different. So I had only 2 before, now I have 3. So the defect is, say, elementary, it's labeled by X. The boundary, the boundary is the second one, is labeled A for the rational boundary condition. So here I'm assuming charge conjugate module invariant, so all boundaries are Cardi-Branes labeled by irreducible fields, irreducible primaries, by primary fields. And so that's A, and then I is the representation which corresponds to the boundary field. So I have 3 of them, and then the condition I need looks like this. So if this is satisfied, then the TDL passes through and just multiplies it by a number. So it's local. So we looked at this problem with Vasilis. And so we showed that, again, unfortunately, we did. So we have, to cut the long story short, we haven't found any non-trivial solutions in the sense that everything, at least one of these 3 representations must be a simple current. So not maybe very interesting, but we showed it rigorously. So we showed for SU2, and as a result for minimal models, so we could find all such triples. And we also did for SU3. So fusion rule, if you want to prove something rigorously, then it's not so straightforward. But for SU3, there is an explicit fusion rule formula, which we use. So, and then essentially it's a brute force proof that, again, we classified all these triples, and in some sense, nothing exciting was found. But I think it's an interesting, again, maths problem, just to try to, so there's some interesting geometry which arises when you look at this fusion condition and try to find some solutions. But certainly sort of, I think it was as far as we could go, with our knowledge. So that's it. I just mentioned some open questions. I have never seen constraints on combined bulk plus boundary flows. I think it would be really nice to, if someone looked into that. Another thing, multi-coupling flows. So if you have several couplings, but in this context, they'd better be all operators in some, say, in the same group multiplied, or at least with the same quantum numbers. But it's easy to arrange in the case of boundary conditions when you start with some boundary condition changing operators. It's easy to have operators organized in some subspaces, linear subspaces. Then one can also find some, one can look for invariant subspaces and derive some constraints on these multi-coupling flows. And then I think it will be really interesting to develop the translation invariant defects rather than the constraints from translation invariant defects rather than from topological defects. And that's something which Jared talked about in the first day. So I think this is one thing that this looking at translation invariant defects can provide. It can provide for you some symmetry enhancement, because those defects always flow to something topological in the bulk. So in this approach here, I would discard it because it wouldn't be, it wouldn't stay topological throughout the flow. But nevertheless, if it commutes with the Hamiltonian, it is still some charge, and it can enhance your theory in the infrared, which will give you larger set of constraints for G flows. So basically, with that, I stop. Thank you.
We have time for maybe one quick question.
So for bulk RG flows, if the symmetry is non-invertible, the people show that the quantum dimension is preserved. So what happens if you have a boundary? Is something similar?
I mean, for these junctions, see, they're really more like local operators. So you can multiply by a number. So I don't know how to extract. I have the junctions, right? And this endpoint, there's a vector space sitting there. So I can normalize them, but I don't know how to extract some number specific to the junction.
Something like a half circle?
Well, usually we normalize it like to these kind of bubbles, half circle. It would just be one. So in fact, I need to keep this normalization. I mean, it's a choice. Normalizations are a choice, but I don't know how to get some procedure which would produce for me a number from a junction. I doubt there is one.
Okay, let's thank Anatoly again.